We will continue our study of functions by studying the behavior of functions. So the rate of change describes how an output quantity changes relative to the change of the input quantity. The units on a rate of change are output units per input units. The average rate of change of a function y equals f of x over the input ab is given by delta f average equals delta y over delta x, which is f of b minus f of a over b minus a. So the delta represents a change quantity. This is the Greek letter delta, and it represents a change. Right? So this is actually change of f, and this bg down here represents an average change. Then this would be change in y over change in x. So we're going to use the data in the table below to find the average rate of change of the price of gasoline between 2005 and 2012, and then again between 2007 and 2009. So between 2005 and 2012, the average change in price, let's represent that as delta P average, would be the price in 2012, which we can see is $3.68, minus the price in 2005, which is $2.31, all over the change in year. So 2012 minus 2005. So we wind up with 1.37 over 7, and this will wind up being 0.20. Now for units, it's dollars per year. So the average rate of change of the price in gasoline between 2005 and 2012 was about 20 cents a year. So increased by 20 cents every year on average. If we now look at between 2007 and 2009, so we go, okay, well, price in 2009 was $2.41. In 2007, it was $2.84 over the change in year. So we get negative 0.43 divided by 2, and this winds up being about negative $0.22 per year. Now we look at this and we ask, does this make sense? A negative rate of change means that the value was decreasing on average. So what this is saying is that between 2007 and 2009, on average, gas came down 22 cents a year. So negative value does make sense. The electrostatic force measured in Newton between two charged particles can be related to the distance between the particles in centimeters by the formula F of D equals 2 over D squared. We will find the average rate of change of force if the distance between the particles increases from 2 centimeters to 6 centimeters. So in this case, we want delta f average? Well, this would just simply be f of 6 centimeters minus f at 2 centimeters divided by the 6 centimeters minus the 2 centimeters, right? So it's the change in force divided by the change in distance. Well, now we have to use this. So f of 6 would be 2 over 6 squared minus f of 2 would be 2 over 2 squared all over 4. So we get 2 over 36 minus a half all over 4. So it's 1 over 18 minus a half, all divided by 4. So 1/18 minus a half. So remember, to subtract fractions, we need the least common denominator. In this case, the least common between 18 and 2 is 18. So it's 1 minus 9 over 18, and that's all over 4. That simplifies to negative 4/9 over 4. Remember, when you divide fractions, you take the numerator and multiply by the reciprocal of the denominator. So the average rate of change is negative 1/9, and the units, the unit of force was Newton, the unit for distance was centimeter. So we get negative 1/9 Newton per centimeter. Now we'll find the average rate of change of t squared plus 3t plus 1 on the interval 0 to a. So delta g average will be g of a minus g of 0 all over a minus 0. So g of a is a squared plus 3a plus 1, minus g of 0, which is 0 squared plus 3 times 0 plus 1, all over a minus 0 is simply a. So we get a squared plus 3a plus 1 minus 0 squared minus 0 minus 1 all over a. And a can be factored from the numerator. We're left with a plus 3. And now if we notice, we can cancel out the a in the numerator with the a in the denominator, and we're left with the average rate of change being a plus 3. Now, in fact, this is a function of a, right? So I could write delta g average of a is equal to a plus 3. And then what this would allow us to do is, given this function, we can easily calculate the average rate of change over any interval that starts at 0. So for instance, if I said, okay, what's the average rate of change of this function over the interval 0 to, let's say, 5? Well, it would just be delta g average evaluated at 5, which would be 5 plus 3, which equals 8. And you can confirm that by using the actual formula, g of 5 minus g of 0 over 5 minus 0. And go ahead and confirm that you get 8. So now let's look at behaviors of graphs and begin with increasing and decreasing. So we say a function f is increasing or is an increasing function on an open interval if f of b is greater than f of a for every two input values a and b in the interval where b is greater than a. Likewise, a function is a decreasing function on an open interval if f of b is less than f of a for every two input values a and b in the interval where b is greater than a. We will look at a graph shortly to explain this graphically. Local extrema. A function has a local maximum at a point b in an open interval, AC, if f of b is greater than or equal to f of x for every x in the interval a to c. A function has a local minimum at a point b in an open interval, AC, if f of b is less than or equal to f of x for every x in a to c. So this is what's happening graphically. So remember, increasing. F of b is larger than f of a for any two input values a and b where b is larger than a. So here we have increasing, which means if I take a value of b that is larger than a value of a, so let's say we'll take b to be -3 and we'll take a to be -4. F of -3 is larger than f of -4. And same argument over here, it's also increasing over here. So in the middle here we have decreasing. So if we take any value b that is larger than a value a, so let's take b to be 1, a to be 0. So f of 1 is less than f of 0. Now for the extrema. So consider the open interval here. It's negative infinity because this means it goes on forever to -1, let's say. Well, on a graph, you can see, oh, well, there's a maximum, right? So what's happening is, the definition said that f of b is greater than or equal to f of x for every value in that interval. So it occurs that the maximum is occurring at -2, so it says that f of -2 is the largest value for f over the interval. Another way you can look at it, we can draw a circle. No matter how large or how small we make this circle, the maximum will always be that largest value. Right, so I can make it now even larger. Right, and this point here is still the largest value of f in that circle. And a similar argument can be made for the minimum. Right, here's the minimum right here. No matter how large of a circle or how small of a circle you make, within the interval, of course, that value will be the smallest value within it. So let's consider the function 2 over x plus x over 3. We will use the graph to estimate the local extrema of the function and to determine the intervals on which the function is increasing and the intervals on which the function is decreasing. So a quick note, notice here that right here, the graph switches from increasing to decreasing. So what happened? Well, it switched at a local maximum. Likewise, at this point, the graph switched from decreasing back to increasing. So it switched from decreasing to increasing at a local minimum. That will be important when we look at this graph. So here's a picture of the graph. In a separate video, I will go about showing you how to use a calculator to come up with this graph. And I already have 2 points labeled. So in fact, the 2 points I have labeled are the local extrema. So we look and we go, okay, we first want to look for the local extrema, so local max, local min. So the local max, well, we have only 2 choices. It's either this point or it's this point. Well, let's look at this point, right? From the graph, it looks like that this point is the largest over an interval. So this would be a local max. Likewise, this point here is the smallest in an interval, and so this would be the local min. Now keep in mind, a graph, a function can have more than one local maximum and can have more than one local minimum. It's also possible for a function not to have a local max or a local min, or possibly not have either. So the local max occurs negative 2.45, negative 1.63. So the x-coordinate is where the local extrema occurs. The y-coordinate is the value of that local extrema. So we would say that this function has a local max at negative 2.45, and the maximum, the local maximum value would be negative 1.63. Then we have a local min at 2.45, 1.63. And this seems kind of counterintuitive, right? We're saying that the maximum value is negative 1.63 and the minimum value is positive 1.63. But that doesn't make sense. 1.63 is larger. This is where the term local plays. It's only a local minimum value. We're not saying it's the overall minimum value of the function. We'll study that a little bit later. So now we can determine intervals on which this function is increasing and intervals on which this function is decreasing. Well, remember, a function will change from increasing to decreasing at its local maximum. So to the left of the local max, the function is increasing. And you can see that here. What's not clear to see is that it actually begins to decrease to the right. That's because we'd have to actually zoom in. And again, in a separate video, I'm going to show you how to do all this. So we'd say it's increasing from negative infinity to negative 2.45. But it's also going to be increasing to the right, positive 2.45. So union with 2.45 to infinity. decreasing, so it decreases from negative 2.45 to 0, and then again from 0 to positive 2.45. Let's now turn our attention back to the toolkit function. Now we're going to look at the tool functions in the eyes of these terms that we just learned. So the constant function is neither decreasing nor is it increasing. It's just a constant. Well, this means that it's not going to have a maximum or a minimum value. The identity function is a strictly increasing function, right? There's no point at which it turns to decreasing. So there are no minimums or maximums. The quadratic function x squared, so it's increasing on the right-hand side, so 0 to infinity. It decreases on the left-hand side, so minus infinity to 0. And there's a minimum at x equals 0. The cubic function is a strictly increasing function, which means there's no local extrema. Well, it's hard to tell, but if you actually zoom in around the origin, you can see that this line never actually flattens out. The rate of increase just diminishes, but it will still be increasing. The reciprocal 1 over x is a strictly decreasing function. So negative infinity to 0 unioned with 0 to infinity, right? Remember that 0 is not included in the domain. Reciprocal squared, so it's increasing on the left-hand side, so negative infinity to 0, and it's decreasing on the right-hand side, 0 to infinity. Now, since 0 is not included in the domain, 0 is not a local extrema point. The cube root function is a strictly increasing function. The square root function is also strictly increasing. The absolute value function, it is increasing from 0 to infinity, decreasing from minus infinity to 0, and the local min occurs at 0. By the way, this also has a local minimum at 0. We conclude by looking at what an absolute extrema is. So the absolute maximum of a function at x equals c is f of c, where f of c is greater than or equal to f of x for all x in the domain of f. Likewise, for the minimum, f of c is a minimum where f of c is less than or equal to f of x for all x in the domain of f. So contrast this to the local, right? To be an absolute maximum, a function can have only one absolute maximum, and it is the largest value of the function over its domain. Likewise, a function can have at most only one absolute minimum, and that is the smallest possible value that function can take over its domain. And so that concludes our study of the behavior of functions.